G'day, this video is the playbook on regenerative nitrogen management. We'll be going over everything you need to know about nitrogen, including the soil chemistry of nitrogen, how nitrogen is converted into proteins in the plant and all the processes along the way, and the minerals needed, and what I look out for as a regenerative consultant. We'll be going over the problems of nitrogen and potential solutions to manage nitrogen in a regenerative way so that we don't lose yield. And we can also improve our nitrogen use efficiency. So this is going to be a really big video, and I'll be going over everything I know about nitrogen completely for free just for you. And if you'd like to see this video in a bit more of a written up format, you can head over to our website and you can see it completely for free. There, everything we've talked about and all the equations and everything written down. Awesome. So the very first thing we need to know about nitrogen is actually what it's used for in the plant. So the most important component of nitrogen is that it makes up proteins or makes up amino acids, and the amino acids get built into proteins. And really, that's the major component of nitrogen. So nitrogen goes into amino acids, which makes proteins. Proteins is a big, broad term for a whole range of different things in the plant. Now, proteins have a lot of functions in the plant. There's enzymes, which help with processing different things. And the structural proteins. Proteins really make up the majority of the plant. So in terms of the amount of nitrogen used in the plant, it's about 1 to 5% depending on the plant and the species. But really, it makes up majority of the plant. Right after carbon, hydrogen, oxygen, nitrogen is the next largest component of the plant. Now, after proteins, there's a few other functions that nitrogen play. The next most important one is chlorophyll, which is, you'll see it here. It circles the magnesium, and this is used for photosynthesis. So it's a very important molecule or component of the plant. It also has a role in nucleic acid and phytochemicals and secondary plant metabolites. So it's really used in a whole wide range of things and very, very important in terms of the produce or what we produce as farmers. Nitrogen is important, so for grain production, it's a protein percentage. That's quite important. In pasture production, the higher the protein percent in your pasture, the greater the weight gains you're going to get on your livestock. And likewise for all horticultural products, you need nitrogen for fruit fill and developing an actual product. So nitrogen is very important, and typically we are usually limited by nitrogen availability for our plants and or water availability. So really these two, water availability and nitrogen availability, are the two main limiting factors for production. And so that's why nitrogen management is really important, because it has a massive importance on our production systems. Now there's a few other things we'll get into, like the inefficiencies of nitrogen applications. So let's start off with, where do we actually get nitrogen from? So nitrogen is in two forms in our soil. It's in an inorganic form or an organic form. And so the inorganic form just means that there's no carbon attached to the nitrogen, whereas our organic form means there's a carbon component, which typically comes from a living organism. So in the inorganic component of nitrogen, we've got two forms. We've got ammonium and we also have nitrate. The main difference between these two forms is that ammonium is a cation, so it has a positive charge, and nitrate is an anion, which means it has a negative charge. And because of those two things, we get completely different characteristics of our nitrogen in terms of our soil behavior and the way it works in our plants. Now, the first thing is how they are stored in our soil. So ammonium, because it has that positive charge, actually attaches onto our clay colloids, so the negatively charged sites in our soil. So it can attach onto our clay, which means we get very little loss of ammonium unless it volatilizes into ammonia, which then can be lost into the atmosphere. So typically ammonium is in equilibrium with ammonia. So we can sometimes get that as a loss, which looks like that. It can be in the soil, but then it can also gas off into the atmosphere and it's lost. So that's a form of loss of ammonium. We'll touch on that a bit later when we talk about urea. But typically this is more or less a stable form of nitrogen when compared to nitrate. On the other hand, ammonium can also attach onto the negative sides of our soil organic matter, which is a really important way to store our nitrogen. Now you can also get a little bit of ammonium in the soil solution, so that's the water within our soil. But the main form of nitrogen in that is our nitrate. So nitrate, because it's an anion, doesn't really stick to any negative sides because it's a negatively charged particle of itself. Typically, this will hang out in the water solution, or it'll be attached onto our soil organic matter on the positively charged sites. Now, because nitrate isn't attached to anything in our soil and it's simply in the solution, it's quite easy to lose this form of nitrogen. The first one is through leaching. So with excess water, that nitrate basically goes down into the subsoil and is lost into the groundwater or anything like that. So that's a really common way to lose nitrate. The other common way is through a process called denitrification, where it's lost as nitrogen gas back into the atmosphere. There's one more process called nitrification, where ammonium is converted into nitrate, from which it's then easily lost. And so this occurs because microbes convert that ammonium into nitrate. But it first converts it into nitrite, which can be toxic. Well, it is toxic in the soil for our plants. So that's the inorganic nitrogen, and it was typically thought that plants only take up these two forms of nitrogen from our soil. But up till I think more or less recently, or the last 10, 20 years, we've been finding out that plants can actually take up organic nitrogen. Now, there's a few different forms of organic nitrogen. The main two big sources are amino acids and amino sugars. Now, organic nitrogen comes from pretty much two sources: microbial biomass, which is all the microbes eating nitrogen, so such as ammonium and nitrate, and converting that into their own bodies. And then when they die or they produce byproducts, it comes out as organic nitrogen, or the decomposition of organic material such as litter or manures. Now, the really beneficial thing about the organic nitrogen is that the plants can actually take up the whole component, so the whole amino acid, and use that. And then we'll talk about the importance of that and why it's so beneficial a little bit later on. But just in terms of the charge, the organic nitrogen doesn't have any charge, which means it doesn't have an acidifying effect on our soil like, say, ammonium does, because when the plant comes, it has to exchange a hydrogen ion for this ammonium. So it creates more hydrogen in the soil, which means it's going to acidify it a little bit. When you have organic components or organic nitrogen, it can just simply take that because it doesn't have a charge. Now, a lot of this information comes from this excellent book called Mineral Nutrition of Plants. Highly recommend it. It's a pretty thick book and it's pretty expensive as well. But if you're interested in all of this, and I mean all of it, like this book goes into a lot more than what even I understand, then it's a worthwhile investment, as well as all the other minerals and how the microbes interact with those. And a lot of this information is based on some of this book, and as well as a few other sources. Now, the other thing about organic nitrogen is that it's very difficult to lose through these different processes. So it doesn't really leach because it's a much larger compound. It's attached to all these carbons, which means it's more or less fixed in place, or it's stored in microbial biomass, and they don't really move that much. So this form of nitrogen is considered very stable. Unless it's consumed and then converted into our inorganic nitrogen, it's more or less pretty stable. It actually makes up a very large component of most soils, and even a larger component in our healthy soils. And finally, our soil organic matter can decompose into our organic nitrogen that can then be used for our crops. Now, soil organic matter contains about 5% organic nitrogen, which is pretty good. My understanding is that about 3% of that, or 2 to 3% of that, gets released each year through mineralization into organic nitrogen, and as well as our inorganic forms of nitrogen for the plant to then use. So if you're wondering how much of these you actually need in your soil, what you can do is get a soil test. I would recommend the Haney soil test, and we'll go over just in a moment why that's important. But if you do have a soil test, we have a free tool on our website. We have the soil test analyzer tool, which uses a CEC style soil test. We also have our Haney soil test analyzer, which analyzes Haney soil tests. We use both of these in our consulting programs. In terms of both of them, what we're really looking at for our ammonium is for this to be around 18 parts per million in our soil, or at least in our topsoil. And then we're also looking for about 13 parts per million of our nitrate. So 13 parts per million. Now this here, these two numbers are from our extractable nitrate and ammonium. On the Haney test, there's two different measurements for it. There's the extraction using the H3A measurement. And so the really beneficial thing about the Haney soil test is that we actually get an estimate on the organic nitrogen that's available to the plant. And that comes from the water extraction technique. So it's just looking at the organic nitrogen in the water, in the soil solution, or stuff that's really easy to extract with a very, very, very soft extraction technique, which is water. And so our organic nitrogen, we want it around the 50 parts per million on our soil test. And you'll see here, 50 versus 18 versus 13, we have a lot more organic nitrogen in our soil than inorganic. Now, obviously, the more organic nitrogen we can get in our soil, the better. It's better for our plants. We'll touch on that at the moment. But it's also not a bad thing to have a bit of ammonium and a bit of nitrate, and we'll touch on that in a moment. So really, it's all about a balance. If we have too much ammonium, that's going to cause problems. If we have too much nitrate, it's going to cause a problem. I don't know if organic nitrogen can be too much of a problem, but like everything, too much of one thing's bad. We simply just want a bit of a balance of everything. So they're the numbers we're aiming for. We'll touch on application rates later on in the video in the second half about optimizing nitrogen nutrition in a regenerative form. But just in terms of what kind of rates we're looking at, or concentrations in our soil, we're looking roughly for these. The ideal amount of ammonium and nitrate will change depending on your soil type. So this is for a bit of a medium soil. In a sandier soil, the ideal amount's going to be a bit less, and likewise in a heavy clay soil, the ideal amounts are going to be a bit higher. So now that we understand a bit more about the chemistry of nitrogen in our soil, let's talk about some of the problems with nitrogen. So the biggest one is that basically it's highly inefficient when we apply it. We're going to lose about 50%. That's the general rule of thumb. We're going to lose 50% of our nitrogen that we apply. That's massively inefficient. And the main ways we're going to lose that is through this leaching form or denitrification or volatilization. And they're the main big sources. Nitrogen lockup or immobilization, which this nitrogen is converted into microbial biomass, is not, it depends on how you want to look at it. It's not a problem because the nitrogen is not lost. I think it's quite beneficial because it converts it into the organic nitrogen, so stored form of nitrogen, which we'll touch on why that's beneficial in a moment. So it really just stores it for a little while and then acts as a slow release. Some people think it's bad because it's not in this form, but I don't quite think that's true because that will cycle within 2 to 3 months. So the inefficiencies of nitrogen applications is not ideal as a problem. The other thing is that if we're leaching our nitrogen away, that nitrogen needs to go somewhere. Typically that will go into our waterways, which can cause nitrification or algae blooms. It's not great for our waterway health, and it can cause a whole bunch of environmental problems too. There's also a really big problem with attracting pest and disease when we have excess nitrogen in our plant sap. We'll talk about that in a moment and how to fix it. Excess nitrogen applications can also burn up soil organic matter. So soil organic matter prefers a ratio of 10 to 11 parts of carbon to 1 part nitrogen. So if we apply more nitrogen, which means carbon needs to be lost for that nitrogen to then maintain that ratio. So typically that will happen because microbes get too excited and start consuming carbon so that they can then balance out that ratio, which means we're more or less burning carbon from our soil organic matter. Now, a little bit of nitrogen is good because it allows us to build soil organic matter, but excess will destroy it or burn it up. So that's not good. And the very last problem with nitrogen, especially with nitrate and ammonium, is that you create more or less a dilution effect within your plant. So my understanding is that nitrogen in nature is the limiting factor for growth, and so plants will scavenge as much as they can. Meaning if there's some available nitrogen, they'll suck it up and put it straight into growth. But if you don't have enough of all the other minerals, simply you're putting on this growth, and it creates a dilution effect on all other minerals, which means you can create deficiencies in all those other minerals simply because you have more volume of plant, but those minerals then need to be spread across. So in order to manage nitrogen, we need to understand how nitrogen is used in the plant and different mechanisms that we can influence with different nutritional applications and the form of nitrogens that we apply. This is very important, so pay attention. So on this side, we have how plants can take up nitrogen. So they can take up nitrate, they can take up ammonia, they can also take up urea, as it is either through the roots or also through the leaves. But regardless of how it is taken up, it needs to get converted into ammonium before the next steps. So how can this happen? With ammonium, it is as it is. So it doesn't need to be converted into anything. It's highly efficient, goes straight into the plant as ammonium. Now, too much can cause that toxicity in the plant, and that's not good at all. So we don't want too much. Nitrate is a bit of a problem because it needs to then get converted into nitrite, which is toxic to the plant, mind you, and then converted into ammonium. Now, this system is very energy intensive. It requires 15 ATP, which is the storage of energy for the plant, to convert nitrate into ammonium. Now, keep in mind that photosynthesis produces 18 ATP. So for every nitrate molecule that needs to get converted into ammonium, one process of photosynthesis needs to occur. And so one study from our excellent book over here found that when barley plants were supplied with just nitrate fertilizer, this process took up 23% of the root respiration. So 23% of the energy from the roots went into converting nitrate into, I think it was ammonium. On the other hand, if we just applied straight ammonium, which they did in this experiment with barley, it only used up 14% of the energy from the roots. So pretty much this system uses up twice the amount of energy, or probably a bit more, but twice the amount of energy that simply this system requires. Now you might go, so what, that's the plant's problem. But really, as farmers, we want to maintain as much energy for the plant as possible so that it can put it into producing yield for us. So if we're applying a lot of nitrate and the plant's taking all this energy to then convert that into ammonium, we're losing yield. So this is a really important one, especially when we're trying to chase high yield. We want to make sure our nitrogen source is in an efficient form for our plant to use. Now for this to occur, there's two enzymes. The first one is the one that takes our nitrate into nitrite, and that's nitrate reductase. This requires two enzymes, molybdenum, which MO, as well as iron in the actual enzyme. The most important is molybdenum, and typically soils tend to be deficient in that. And the second one is nitrate reductase, which requires iron and sulfur. The really interesting part about this is that if we don't have molybdenum or iron or sulfur available for our plants to then make those enzymes, our nitrate won't get converted into ammonium, which means if we apply a bunch of nitrate fertilizer, that won't get converted into ammonium. It'll simply stay in the plant as nitrate, which is not great at all. And we'll talk about why that's not great just in a moment. But really, we don't want it there. We want it to flow along this pipeline. And finally, we have urea. Now, urea is actually really good because it's technically an organic compound, not from a certification point of view, but because it contains carbon, which means it's in a more efficient form of nitrogen because it has the carbon that the plant can then, I guess, reuse. So it's a little bit more efficient from a carbon point of view. So in order for nickel to be converted into ammonium, nickel must be present for the enzyme uranase, which allows this conversion. So similar to molybdenum over here, if we don't have nickel and we're applying a bunch of urea, we're going to get urea buildup, which can be quite toxic to the plant, and we're not allowing for this system to occur. So sometimes you don't even have a deficiency in nitrogen, you just have a deficiency in either molybdenum or, if you're applying urea, nickel. When we're thinking about what forms we want to apply these things in, sometimes it's beneficial to have both forms, as the pathways, we kind of want all the pathways to be utilized at once, and that will be most efficient for the plant. So we might want a bit of nitrate, we might want a bit of ammonium, urea, depending on your system, but really want a little bit of each to help the plant. Now, one more thing in terms of nitrate, you'll see here that we add 4 lots of hydrogen onto our nitrogen. The thing is, where does that hydrogen come from? And it comes from water. So water, H2O, there's 2 parts hydrogen in water. It means for every nitrate molecule that we want to convert, we need 2 parts of water for them to get split in half to release that hydrogen for them to get added on. So this system is also more water intensive and will require a lot more water than applying ammonium. Now, on the other hand, when we come back to here, nitrate is only in this water component of our soil, and it's not attached onto the clay colloid, meaning that if you go into a drought, it's more difficult for the plant to absorb nitrate because it's only available in a soluble form. Now, one more thing before we get into the rest of the process is that both ammonium and nitrate will be taken up through the roots. So they go through the roots. Ammonium tends to get converted in the roots itself, whereas nitrate gets taken up into the leaves to then get converted up there. And it doesn't necessarily mean that ammonium doesn't get transported, but it tends not to be. And it also doesn't necessarily mean that ammonium can't get converted in the leaves. So there's a few other ways that ammonium can also be in the leaves. The first one is photorespiration, which is simply when the leaves or the chlorophyll gets overworked and it starts combining oxygen rather than carbohydrates. And that process causes a few problems to happen, one of which requires a byproduct of ammonium to be created. So photorespiration increases the amount of ammonia in the leaves. So you can get ammonia in the leaf that way. You can also get it from the breakdown of proteins, which can happen after a herbicide or pesticide application. It can also happen during senescence. So sometimes you get ammonium up here. Typically, when it's absorbed from the soil, it'll be converted in the roots. Now, because of that, these two plants have very different effects on the physiology of the plant. So the first one is that when the plants take up ammonium, it tends to stimulate root development, and so this can help set the plant up with a larger root system, which can then help with future development later on in the season. The other one is that when nitrate is applied, it tends to stimulate vegetative growth, which can be beneficial, say for tillering. So if you want to increase the number of tillers, the application of nitrate-based fertilizers can assist with that. However, in one study I learnt from Joel Williams was that the combination of the two can actually increase the overall tillering of the plant. So it's not that one is best or the other one is best, it's that the combination of both of them is beneficial, and everything in moderation. But overall, a bit of nitrate will assist with vegetative growth, whereas ammonium will assist with root-dominated growth or reproductive growth, as a few other things found that ammonium can stimulate reproductive growth. So once all the forms are ammonium in the plants, all this has been converted into ammonium. The ammonium needs to get converted into a amino acid called glutamate. Now this is more or less the feedstock for all other amino acids. For this to occur, the ammonium gets attached to a carbon backbone, which is produced from photosynthesis. So it's very important that we have really strong photosynthetic ability of our plant to produce these backbones for the ammonium to then get attached onto. For this process, we need two minerals. We need magnesium and manganese. Both of these are in the, I think it's glutamate synthesase enzyme or something like that. You need both of these. So if you don't have either of these, you're not going to have this process happen as efficiently. But most importantly, you need that carb, you need the sugars from the plants. So when we look at a differential sap test, we'll talk about that in a moment and how we use all this in that. We want to make sure we have really high levels of photosynthesis for our plant to then rapidly convert our ammonium into glutamate. Now this process requires 5 bits of ATP. So when we compare 15 bits of ATP to convert our nitrate into ammonium and then an additional 5 to convert it into glutamate, applying nitrate is again very energy intensive. If we can just apply it or get it into that ammonium, it's a lot more efficient to then get that into glutamate. But I can't stress this enough, we need to make sure we have enough photosynthates or sugars in order to convert our ammonium into glutamate. So when looking at a differential sap test or even leaf test or whatever, if you're looking at the plant and you've got high amounts of ammonium, you need to check your sugar levels, your bricks or whatever. And typically you find if you've got really high ammonium, you tend to have low sugar levels because this puts a high demand on our plants for sugars to convert it. So once we have our glutamate, that glutamate can then be used to produce other amino acids. For this, some of them require sulfur, so methionine and cysteine, they require sulfur. So in order to produce basically all the amino acids that the plant needs, and the plant can produce, I'm pretty sure all of the amino acid it needs sulfur to produce those other two. So it can produce sulfur containing amino acids as well as all the other ones, and we get left with our amino acids. So now we've got a bunch of amino acids. They can get put into what's called a polypeptide chain, which is a chain of all these amino acids. That gets bundled up into a protein. Now for that to occur, we need a whole bunch of minerals. We need magnesium, zinc, potassium, phosphorus, manganese, and boron. All those are important for the amino acids to then get converted into proteins. And really, this is where we want all our nitrogen to be stored in. We want it all to be pushed into our proteins because at this stage, it's actually usable for our plant and we're not going to have as much pest and disease pressure. Now, remember back to the first part of the video, we talked about how plants can actually take up amino acids. So the most efficient way that plants can get nitrogen is from amino acids because it goes straight there. It bypasses this whole process, wasting 20 bits of ATP plus whatever it needs to convert glutamate into amino acids, and just supplies straight amino acids. So this is a highly efficient way to get our nitrogen straight into our plant as what it needs already. And it skips all this conversion and problems that we get with that. Likewise with the amino sugars, I'm not too sure about the conversion process, but I'm assuming to break up the sugar part from the amine that would require a bit of energy, but because you have all that carbon, a lot more efficient than, say, supplying it with nitrate. So one of the big things with this, and if you think back to the video, John Kemp's plant health pyramid, we want to make sure we're supplying more or less 100% of our plant's nitrogen requirements as amino acids or as microbial metabolites. And that's because we save all this energy from converting nitrate and ammonium and urea. Now, this process only occurs from having a really healthy soil full of organic nitrogen and full of microbes that can supply the plant with amino acids and even potentially proteins. And this is kind of what we aim towards with our regenerative systems, increasing that organic nitrogen component with a really good biology. And we'll talk about where we can get some of that biology and the rhizophagy cycle in a moment in terms of our fert options. But this is really important. Now, I put up all these minerals just to demonstrate that it's not just nitrogen that we need to apply, but all these other minerals as well to ensure the nitrogen actually gets converted into our proteins. So we need our sulfur, we need our magnesium, we need zinc, we need molybdenum if we're applying a lot of nitrate forms, we need iron, sulfur, nickel if we're applying urea, all these different things in order to get our nitrogen from our inorganic forms and put it into our proteins. If we're missing any of these components because they're deficient, then we're going to have problems and we're going to be losing yield. So really, when we're thinking about regenerative nitrogen management, we're not just thinking about nitrogen, we're thinking about the whole system, we're thinking about all the minerals required in that. So once we get it into a protein, it can then be used for whatever the plant needs. You can put it into grain fill and increase the protein content in that, or plant defense compounds or whatever. But this is where we need to get it. And this is also where we need all of our nitrogen to be stored in order to prevent pest and disease pressure. Now, that might sound weird if you're new to this, but simply pest and disease are seeking nitrate in really simple forms, really in these two forms, as well as potentially amino acids, depending on the complexity of the pest and disease digestive system. A lot of pests don't contain the enzymes required to break down proteins. So proteins over here, they just need really simple forms of nitrogen, the inorganic forms, which means if our plants contain a large amount of these, because they're not stored as proteins, then we're going to get lots of pest and disease pressure. And so there's two really good books on this. The first one is Healthy Crop. That's a really good one that kind of highlights this whole idea, as well as Tuning into Nature, which is more about signaling or how plants and insects can communicate through infrared signals. And so this is how it works. You got, say, a high buildup of nitrate or ammonium in our plant sap, or in our plants as it is. We'll have a bug over here that's flying around doing bug things. That bug will sense that this plant contains a lot of food stock for that bug, and it will be attracted from that. Some people suggest it can be up to 2 Ks, the distance that the insect can detect these inorganic compounds, and it can basically hone in and attack those plants. And so, to some extent, you actually get some paddocks where the farmer's been practicing these regenerative or organic systems, and they don't have much ammonium in the plant. And these pests will just simply not even attack those paddocks. They'll go to the neighbours' paddocks and destroy their crops. This is a really important component of disease and pest management from a regenerative point of view. We don't need to be applying pesticides because our plants aren't food sources for pests in the first place. And really, in order to achieve this, we need to make sure that these are converted into proteins in our plants, which means we need all these minerals as well as large amounts of sugars to produce the feedstock for this conversion of ammonium into glutamate. Now, remember when I was talking about photorespiration and protein decomposition, a lot of that can actually occur when you apply herbicides or pesticides, meaning that if you apply a pesticide, typically, and this is what they explore in Healthy Crop, you actually get protein breakdown and it prevents, as well as the prevention of protein synthesis, which means you can actually build up your ammonium in your plant, in your plant sap, meaning that it becomes even more favorable for insects to attack your plants. So, interestingly enough, more herbicides you apply or pesticides, the more pesticides you'll need because your plants produce more ammonium to attract more plants, which means you need to apply more herbicides and pesticides. which means your local chemical rep gets more money. So breaking the system and making sure that all of this is converted into proteins will really help reduce pest and disease problems. Now, one more thing before we move on, I don't necessarily think it's bad to apply these things so long as we convert it into proteins rapidly and we give it everything else. Now, it's ideal to be applying it as amino acids, but amino acids are expensive. Urea is a great way, but it goes straight into ammonium. Is making sure that we have the process set up so that the plant can then rapidly convert that into proteins every 24 hours to prevent our pest and disease. So I mentioned a thing called differential sap test analysis, and that's something that we do in our consulting. What this does is looks at the sap concentrations of, we'll just talk about nitrogen in this case. We'll look at the nitrogen concentration in the sap itself, and it will determine, and it can help us understand whether or not it's deficient. And we use the differential part, which allows us, we compare the young and mature leaves of the plants. Now we know that nitrogen, when it becomes deficient in the plant, we'll say it takes the nitrogen from the oldest leaf and then puts it into the youngest leaf because it's more efficient from a photosynthetic point of view, as the younger leaves are more efficient. And so it's worthwhile the plant having more nitrogen in the younger leaves because it can produce, it can photosynthesize better than in the old leaves, which can get shaded out. So the plant will move nitrogen from the old leaf into the new leaf, which means if we take a sample up here and a sample down here, we compare the levels, then we can actually determine nitrogen deficiencies or sufficiency in that case. So if you do have your own test, you can actually use our free differential sap test analysis tool on our website to help determine whether or not you have a deficiency or not. But really what we do, we don't use threshold values because there's a bit of a problem in terms of what the lab does is that they get all their samples for that particular variety or species and the average amount. So you're not really getting what the plant needs. You're just saying the average of all crops is this, so it should be about that. So we just compare the different values with what we call the YO value, so young over old. If there's a more than 10% variation between the young and the old value, that would suggest to us that the plant is starting to move nitrogen from the old leaves into the new leaves, which signals to us we should maybe apply a nitrogen foliar to supply the plant with a bit more nitrogen. Now, in the differential sap tests that we get 4 values that is of interest in terms of this. The first one is that we get our sugar percentage or bricks, depending on the test. This is important because it directly relates to this process and photosynthesis. So we get sugar, which is quite important. We get nitrate. You don't want any nitrate because it signals to our pests, come eat me. So we don't want any of that. So really, on our test, we actually want this to equal 0. Likewise, it gives us our ammonium. We also want that at 0. So we want 0, 0 for both our inorganic nutrients. But now you might be thinking, how do I actually determine how much nitrogen we have in the plant sap? And that's why we have total N on the tests as well. And that's really what we base our deficiency or sufficiency ranges on. And it's this number. Typically, it'll be, depending on the plant, in the ballpark of 3,000 to 4,000 parts per million of nitrogen. And the thing is, this considers our amino acids, proteins, as well as peptides or whatever. It's the total amount of nitrogen in the plant sap, as well as our inorganic forms. But if these are both at 0 and this is at, say, 3,000, then we know that there's 3,000 parts per million of protein or amino acids or organic nitrogen in the plant sap, which is really good. Likewise, so if this is our young value and our old value is 250, when we compare these two numbers, we can see that the old value has less, is pushing nitrogen into our young leaves. That would suggest to me that we have a deficiency and we need to get something on our paddock. Again, you can use our free calculator to do that, or you can just do it yourself. This is really beneficial using the Go value because it doesn't matter what crop you use, what stage of the crop. Really, we're just looking at where is the plant allocating nutrients and then determining deficiency and sufficiency ranges from that. Our free calculator also tells you whether or not you have a slight deficiency, a moderate deficiency, or an extreme or severe deficiency. It'll also give you a range, high, medium, low range on your foliar applications. So it's a good tool. It's completely for free, so you can check that out. Now, we also use the differential SAP test to determine what of these minerals we're deficient in. So say we have a high amount of nitrate, we can look at that and go, okay, our sulfur levels are fine, our iron levels are fine. What are we missing? Oh, it's molybdenum. We can actually see that on the tests. We can also compare that to our soil test and go, do we have molybdenum in our soil? And if there's a lot of molybdenum in the soil, but it's not getting to the plant sap, there might be something else blocking that. So we take very much a holistic approach in terms of our nutrition. We look at our soil tests, we look at totals. So is there a total amount of molybdenum? Is there anything available? Is there anything in our plant sap? All of that gives us a really complete understanding of the nutrients that the plant has available and what it's picking up and what problems we need to solve. Now, you can do the same thing with a tissue test. Now, there's a bit of a difference with that, but really we're just looking at the variation between our young and old leaves. This is really beneficial because it can tell you a deficiency up to 2 weeks in the future before you actually see any signs of a deficiency on your plant. Once you see a sign of deficiency in your plant, you will really begin losing yield. So we can use a differential SAP test before we're losing yield. So that's very beneficial. So the final part of the first section of this video is our fertilizers. What different forms of nitrogen can we get? And we'll talk about how this kind of relates to this process. After this, we'll be going into different regenerative solutions that kind of overcome a lot of this. So we have a whole range of different forms of nitrogen fertilizer. Each are beneficial or negative in their own right. A lot of these you can actually mix into water and create a foliar application. So a lot of these, you can either apply as a solid, depending on whether or not it's a solid, or you can mix into water, create a solution and apply it. First one, urea. Urea, as we said, it's great as a foliar, very problematic though as a soil applied amendment. The reason is that basically once we apply urea, if it sits on the surface, it can then convert it into ammonium and then ammonia, which then volatilizes and you lose it. So a lot of the times you actually lose urea if you apply it outright, and you do need a bit of rain to then dissolve it into the soil. So once it's in the soil, it can dissolve into ammonium and then stick onto our clay. It's still pretty much lost a lot of the time, but it's less loss. So this is quite inefficient when we're applying it as a soil amendment or a soil application. Now, the other thing that's a bit of a worry is that ammonia is toxic to our plants. So there's a risk that you can damage your plants with applying ammonium products because it creates ammonia. So you might not want to apply that as a starter because of the problems associated with ammonia. Really just depends on your system, your soil, your different environments. But urea actually makes really fantastic foliar. And so you can apply that, I think it's in the range of 5 to 10 kilos per hectare of urea as a foliar. It's very efficient. It's suggested that it's about 7 to 10 times more efficient than the soil applied. Anyways, then we have sulfur of ammonium, so ammonium sulfate. Simply, we get our ammonium as well as some sulfur. So that's quite beneficial if you want to get some sulfur in the system. We talked about the importance of sulfur here and here. So a bit of sulfur is a good thing. MAP, so with this one we get a bit of ammonium as well as phosphorus, which is quite beneficial. So we have MAP, which is mono ammonium phosphate, and then we have DAP, which is diammonium phosphate. So we have 2 parts of ammonium. In DAP, MAP, we've got 1 part. We still get the phosphorus. We can actually use these in a foliar application to supply phosphorus to the plant. Next we have urea ammonium nitrate. So that's basically all of it together. It comes in a liquid form. You can foliar apply that as well. We get a bit of everything. So in terms of when we talked about we wanted a little bit of everything, it's not a bad way of doing that. So really there are a lot of our forms of ammonium. And remember when we talked about ammonium stimulates more reproductive growth or root development. So that's quite beneficial. And then we have more or less our nitrate forms. So calcium nitrate, both of which stimulate vegetative growth. The calcium is quite important from a quality of vegetative growth component, but again, we have that nitrate too, which means we're going to get a bit of a dilution effect, which might not be a bad thing if you've got excess minerals everywhere and you just need to kind of bring everything down, or if you want to stimulate a bit of tillering or vegetative biomass. Next is potassium nitrate. Again, you can use that as a source of potassium as well. All of this, except our urea. Urea is technically organic in terms of a chemical point of view. All of this is more or less inorganic. Next, we've got our organic forms. So that's protein, amino acids, hydrolysates, which is pretty much a breakdown of organic components. So if you think of like fish hydrolysate, that is the fish. It's fish broken down under different enzymes and acids into more or less the bare components. We've got manures, we've also got microbes. So each have their own benefits in terms of foliar applications or soil applied. Manures, you can't really foliar apply that. These are all quite beneficial because we supply our nitrogen in this form as amino acids. So rather than applying it up here, we apply it here. Manures can release a fair amount of ammonium and nitrates, but it can also have amino acids components. The most beneficial, and the thing that we really want to get to, is the microbe component here. The microbe component is what we get from the rhizophagia cycle, which is where the plant will actually consume microbes into the root, rip off the cell walls, which contains a lot of amino acids, as well as calcium, a whole bunch of minerals, and it'll actually spit out that enzyme back into the soil. So it's very beneficial to supply our nitrogen from this point of view because it supplies our amino acids straight to the plant and then straight into proteins. So we can actually supply, in one study they found that you could supply about 33% of, I think it was a tomato plant's nitrogen requirement from the system. I think that was in a lab environment. So I think there's a big potential to supply a large amount of the nitrogen requirement for the plant. 33% in that study, might be more, might be less, depending on your situation and the biology within your soil. Another form of nitrogen we can get is from decomposition, but the decomposition of plant biomass. So say nitrogen from legumes, they're all sources of organic forms of nitrogen. So again, depending on the goals and some of the other minerals you're trying to chase, as well as whether or not we're trying to chase a reproductive stage or a vegetative stage, as well as the cost of all these, will depend on what we're applying. There's a whole range of different reasons why we might go for one over the other. And I wouldn't say any are bad, just different. And we really need to adapt our nutrition programs using these different fertilizers as tools, rather than saying, calcium nitrate is bad because it contains a nitrate, which is going to attract insects. We're going to use that more of a tool depending on the situation. Of course, getting as much from our microbes is beneficial because of this, but I wouldn't completely scrap all of this because of that. Now, one more thing before we go on to the solutions from a regenerative point of view to solve all of this, is that mineral interactions from the soil. So we have our cations here. Pretty much all cations will share similar uptake pathways in the plants. What will happen if we have too much ammonium in our soil is that it competes with all our other cations, so calcium, potassium, magnesium, for those uptake pathways, which means if we have too much ammonium in our soil, it'll antagonize all the other minerals or all our other cations to prevent them from being taken up by the plant. Likewise with nitrate, that will antagonize sulfur, phosphorus, boron for its uptake because it's ion and they all share uptake pathways. Now, just a warning in terms of the application of nitrates. Because it stimulates vegetative growth, you can get really long and straggly plants, which you don't really want. You want a nice compact plant, which is more root dominated. So you don't really want to be stimulating vegetative growth too much. You want to make sure you got really good roots supporting nice dense vegetation. It can be beneficial, again, if you're trying to stimulate tillering in wheat and your cereals. But overall, we probably want to make sure our plants are root dominated or reproductive dominated than vegetative dominant. All right, so now let's get into the solutions or the regenerative solutions that we consult on for nitrogen management. So now let's actually get into managing our nitrogen in a regenerative way. And the very first thing we want to start with is a good nitrogen budget. So I typically find nitrogen is the limiting factor for a lot of regenerative growers. Typically what they do is they hear that you don't need to apply as much nitrogen and they cut it by half, which is not the right thing to do. And typically your soils need to be built up to the point where they can actually supply your crop with the majority of its soil. But it's very important to take a scientific approach to all of this and not throw out all the agronomic textbooks. So the very first thing we want to do is develop a nitrogen budget. What we need for that is first a yield target. Now, if you're already using just historical data, that's fine. What I like to do is start from scratch and go, okay, what is the theoretical economic yield potential for our region or our area, and then go off that. That way, we're not using kind of previous data that might be actually inaccurate because of previous farming systems or previous management practices. We've got a video on estimating yield targets. It's a previous video, so go watch that out to develop a yield target for your area using rainfall data. And we'll go through this now. So we're going to estimate a yield target of about 4 tons a hectare. And next what we want to do is, now this is an example for wheat, but this applies to any other system that you might be running, whether or not it's livestock and you're estimating pasture production, so you have your yield target, and we'll work through this, or if you're doing apples or whatever. We have a yield target, which basically just biomass produced. We have our nitrogen per ton of that, so basically our removal rate. Now, you can get really technical and go, okay, what is our protein percentage, which is what we're going to do here. So we've got our protein percentage times that by 1,000, so 1 ton is 1,000 kilos, and then 16% is the amount of nitrogen per unit of protein. So you can either do it like that, where you're actually estimating the amount of nitrogen per bit of protein that you need to apply, or you can just use a typical estimate for your crop. So typically people go on a rule of thumb of 20 or so for wheat. You can actually estimate it depending on the protein goals. So we're going to say we want a 13% protein in our wheat. So it'd be 13 times 1,000 times 16, which is equal to 20.8 kilos of nitrogen. What's that, per ton of biomass. Now the general rule of thumb is you're going to double this rate, because half of that nitrogen is going to be lost anyway. So we're going to do that and then pretty much change everything else on the other end of our calculation to be the equivalent of that. So we'll times that by 2, and that is effectively how much nitrogen we need. So work that out. So that works out to be 166 kilos of straight nitrogen per hectare to grow a 4-ton crop. So regardless of your system, you have to apply 83 kilos of nitrogen to the crop. There's no way around that. You have to apply it, because the crop itself is actually exporting 83 kilos of nitrogen. So you have to supply it with that nitrogen. The question is, how do we actually supply that crop with the nitrogen it needs, like it physically needs? Because you know what's not regenerative? Not actually producing a crop. And so if we don't supply the nitrogen, we're not going to produce a crop, which is not very regenerative to our bank accounts. So the number one thing that we need to do as farmers is actually produce a crop that we can sell and make money. The question is, how do we do that in such a way where we can make money and not be damaging to our environment and improve the system at the same time? Now, another really important thing is that you need to optimize your production, potentially not maximize your yields, but you need to optimize your yields, because you've got a certain amount of overheads, regardless of your yield, you're still going to run your header over. It's still going to burn X amount of fuel. So really, you want to optimize your production to maximize your profit, which typically comes with higher yields. So you don't want to skimp out on yields, but you do need to optimize it. Cool. So the very first thing we've done is we estimated how much nitrogen we actually need to supply to the crop. And so the first part of this is we actually want to know how much nitrogen is in the soil ready to be applied. or supplied to the crop. So remember from the previous section, there's three main forms of nitrogen. There's nitrate, ammonium, and organic nitrogen. We can actually get these from our soil tests. We use a Haney soil test because it incorporates that organic nitrogen component, which is very important, and you'll see why in a moment. So using some example data, let's just go with, say we've got 13 parts per million of nitrate, we've got 18 parts per million of ammonia, and then 20 parts per million of organic nitrogen from our Haney test. Now, if you do have a Haney test and you want to kind of see all this, you can get a free Haney test on our website. It's an analysis on our website. It'll add all this up together and give you an estimate on the nitrogen for your soil. Anyways, we add all that up and we get 51 parts per million of nitrogen in our soil, or milligrams per kilogram. Now, the next thing we want to do is convert this into kilograms per hectare. The easiest way to do it is you take this number, you times it by the depth of your sample. So say for this one, we're sampling to 10 centimeters. We're going to divide that by 10 times by our bulk density. So for this, we're going to assume a bulk density of 1.4. You can look at kind of standardized charts for bulk density. So it might be ranging between 1 to 1.5. 1.4 is good enough. But anyways, this is going to spit out, 71 kilograms of nitrogen per hectare. Cool. So this is the amount of nitrogen we already have in the soil. So if the crop needs 166 kilos of nitrogen per hectare and the soil already has 71 kilos per hectare, then the difference is what we need to supply to the crop. So to work out the additional nitrogen we need to supply to this crop, we're going to take what the crop needs minus what's already in the soil. So it's going to be this minus 71, and that's going to equal 95 kilos of nitrogen per hectare. So the question now is, how do we supply this 95 kilos a hectare of nitrogen to the crop? Now, there's kind of four things we need to think about when supplying this to the crop, and that's source, the rate, the timing, and the placement. So as we talked about before, source is very important. Are we applying it as nitrate, ammonium, or an organic source? Likewise, are we going to do that as some starter, or is it a foliar, top dressing, side dressing? How are we going to apply that? The rate is important. Timing is important to match actual crop demand. So the demand for the crop isn't all up front at the seed stage or even seedling. It's when the crop is actually establishing and putting that bulk on. The other thing is place. Where are we going to place it? Are we going to place it right on top of the seed, beside the seed? Where are we going to place it? So all these things we've got to factor in, as well as the price. The price is also very important. We don't want to splurge too much on the finest amino acid foliar sprays because it's just going to be way too expensive. But nevertheless, how are we actually going to get this 95 kilos a hectare of nitrogen to our crop? So from a fertilizer point of view, you kind of have three options. You have your starter, your top, or your side dressing. You can either apply that like as a liquid, so liquid banded application, or you can spread it as a granule. For either one, to increase the efficiency, you can apply 5% of the overall weight of that as a humic substance. What happens is, similar to our organic matter, or the soil organic matter, it has positive and negative sites. The humic substances also have positive and negative sites. So the nitrogen source can actually cling to the humic substance and prevent it from being leached away or volatilized off or denitrified. The other benefit of this is that it gives our plants another additional carbon source to then consume to help process that nitrogen. So a really good way of doing this is you take the price of your humic substance and then subtract whatever that cost is from your nitrogen side, and it should balance out to be the same cost, but improve your efficiency. So that's a really simple one, and that's everything from urea to MAP to DAP, SOA, whatever. That's a really simple one, especially when you're with starter. So if you're going to apply some starter, adding some humic substances up front will help absorb that, also help with phosphorus. We'll talk about phosphorus in the regenerative phosphorus management video. But overall, it just increases the availability and prevents the loss of nitrogen. So in terms of the efficiencies of this, one study found that the addition of humic substances had somewhere between a 35% to 77% increase in the nitrogen use efficiency, which is not bad. So you could probably start to think about reducing your nitrogen applications in order to achieve the same yield by somewhere in the ballpark of 0 to 50%. Now, I probably wouldn't go past 50% because you still need that nitrogen. I wouldn't jump straight to reducing your nitrogen application by 50% just because some random study somewhere in a random location around the world found that they could increase nitrogen use efficiency. What I would do is I would start in your first year by reducing the nitrogen application by the cost of your humic substance. Then in the following year, I drop it a little bit more, then a little bit more, then a little bit more. That way we're reducing the risk while actually building up the other side of the system that we'll talk about in a moment. We need to do things slowly, otherwise there's a risk of losing yield, which we don't want to do at any cost. So that's the first one. We've got just a typical nutrition program. We're going to apply starter, maybe top, side dress. Now, going back to the timing of these, if we can split the applications up, that would be even better for our plants. So think about it. On one side, we can basically front load all of our nitrogen fertilizer in one hit, and the other side of the spectrum, we connect a drip line to our plants and feed in exactly how much nitrogen that plant needs. That's going to be too expensive and labor intensive. This is going to cause problems. Somewhere along that line is the most optimized program. So I guess the next step in from front loading all your nitrogen is split applications. So a little bit at the front, maybe a bit on the top later in the season. That itself is going to improve your efficiency. Now think about that again. Maybe you do a bit up front, a little bit later, and again, a little bit later. So all these kind of things, doing split applications, just depending on the cost of labor and application costs, you can find that sweet spot. Now on the other side of this, if you think of the nitrogen uptake by the plant, look something like this. Where in the first little bit, there's actually not that much nitrogen uptake. In the last little bit, there's also not that much nitrogen uptake. Really, it's all in here. So we really don't need that much up front. It's really at the point of tillering where the nitrogen uptake really increases, and then it gets to flowering where you don't really need too much more. So it's in this stage between tillering and flowering, which is the most amount of nitrogen uptake. So if you can split your applications across a little bit up front to supply this component, just get it tillering, maybe a bit of nitrate to induce a bit of tillering, and then supply your next top dressing or side dressing at the tillering stage. Now that's just in terms of the starter, top and side dressing. The next really interesting thing, and this is a really great way to improve your nitrogen efficiency, is foliar applications. So the problem with a lot of soil applied applications is that the nitrogen is applied to the soil. There's all these systems within the soil that can induce losses as well as disturb different soil microbes and nutrient interactions that inhibit nitrogen uptake, or the nitrogen actually inhibits those minerals that can occur. So applying a nitrogen as a foliar puts that nitrogen straight into the plant rather than through the soil and then through the plant. So it goes straight into the leaf, you apply it to the leaf, goes straight into the leaf. Ultra efficient way of applying it. So some people estimate it's between 7 to 12 times more effective than, say, applying it to the soil, which means when we factor in, say we're applying 5 kilos and we're going to assume so it's 10 times more efficient, that 5 kilos of nitrogen that we apply as a foliar is equal to 50 kilos of nitrogen applied as a starter or side dressing. And there's also a lot of factors that play into getting that efficiency, but overall, when you do it correctly, it's really, really efficient. And so the typical application rate is about 4 to 9 kilos a hectare of nitrogen, of nitrogen in a urea form. So that's not high rates, but again, it's really efficient. Now you don't want to go too high because you can damage the plants, and there's a few different things you can do to actually increase that rate without damaging the plant. So back to thinking about the different pathways, nickel is quite important, especially when you're applying urea. So if you apply a little bit of nickel as well, now it depends. And it's always good to get a soil test that also has a nickel component to it if you're going to really go heavy on this, because nickel is a heavy metal and it can be quite, not dangerous, but you got to take good considerations when dealing with it. You don't need to apply much. I think it's 10 or so grams per hectare, but it's something really got to consider. I think some people I've seen push it up to 20 or so, maybe even more kilos of nitrogen per hectare. So that's a lot of urea. I wouldn't recommend it. I'd stick within kind of a lower range and just kind of see how we go. And there's other ways you can apply foliar nitrogen. So everything we talked about in the FERT forms, so everything from MAP to DAP, anything soluble, really, UAN, ammonium sulfate, all of that, you can, if it dissolves, you can apply as a foliar. With different products with different rates, there's also a few limitations in terms of the pH, EC of the solution, so you don't damage the plant. But really, you can start experimenting with different applications of different forms of nitrogen. Now, the other thing with foliar nitrogen is that different chemicals don't mix together. So urea is highly basic, which means that you can't add it to acidic things. If you do, it creates a sludge at the bottom of the tank. It creates a precipitate, and that's a really big pain to clean out of your spray unit. But anyways, highly efficient, great way of doing it. Now, with every nitrogen application, there's a few things you can add to it to increase the efficiency, and it all relates back to what we talked about before with those nitrogen conversion pathways. And so this is a classic nitrogen efficiency program. What we want to do is add around 3 to 5% humic substances to it. So that could either be humic acid or fulvic acid. Not so much humate because that's not soluble. But generally, this is really good for liquids because you can get a really nice uniform solution, which is quite beneficial for foliars as well as if you're soil applying something. Anyways, 3 to 5% humic substances, about 1.5% molasses. So this gives the energy to our microbes or our plants to then process that nitrogen. And also this is a percentage of the nitrogen product. So say you've got 100 kilos of urea, you want 3 to 5 kilos of humic substances, 1.5 kilos of molasses, 1.5 kilos of kelp. Likewise for any other product, you're taking the kilo of it. So again, with an energy source, kelp's a really good one. It contains a whole wide range of autoinducers and hormones and growth promotions to the plant. So this just helps it really recover. It has a whole wide range of complex carbohydrates. That's beneficial. Kelp's a really good one. So adding a bit of kelp. We want to add sulfur at 10% of the nitrogen component. So this goes back to the development of methionine and cysteine, so the two sulfur-containing amino acids. So it's about a 10 to 1 from nitrogen to sulfur. So we want to make sure we apply a bit of sulfur. So you can do that quite easily by adding a bit of ammonium sulfate to the mix. So if you're using urea and ammonium sulfate in a liquid nitrogen foliar, adding a bit of SOA can help supply a bit of that sulfur, so that's quite beneficial. And next we want to apply a bit of molybdenum. Again, that's going to help with the conversion of our nitrates into ammonium. And if you want, and depends on your soil test, I'd be quite hesitant about nickel, to be honest. Not because it's bad, but you don't want to have too much on your farm because it's a heavy metal. So the application of that is 10 grams per hectare. I would really want to get a soil test done or a sap test to see the concentrations of that in your soil. But anyway, as you can add that to any liquid application, you can add it either as a foliar, so mix all this in with your urea and your SOA or whatever, apply it as a foliar, or you could also apply it as a soil application, get it in before a rain event. So this should be able to increase your efficiency somewhere in the ballpark of 25 to 50%. Depending. It depends on a whole wide range of factors, including your soil temperature or just the temperature, humidity, rainfall, even your soil type, the microbes active in your soil. If you are applying it as a soil application, what I would highly recommend is adding some biology to this. So potentially some worm casting extracts or just really anything. Because when we apply it to the soil, what we want to do is we want to convert the nitrogen in that application straight into microbial biomass. So if we're adding it as urea, we want our microbes to take that urea, take all these other ingredients, and then make amino acids from that. That way, the plant can actually then take up those amino acids rather than urea, which can have problems. Likewise, when we bind it into a microbial biomass, we reduce the amount of losses through leaching and volatilization and denitrification. You can add microbes maybe in a foliar application. They are quite beneficial, but it really depends. So that's kind of the two components of our fertilizer itself program, and increasing the efficiency of that. Now, it really has a lot to do with carbon and making sure we've got enough sulfur and even sugars and whatnot to supply the plant with that energy and to prevent that nitrogen from being lost. So when we work with farmers through our consulting program, what we do is we run through a framework called ESR. So this stands for efficiency, substitution, and redesign. So we don't quite want to take a farmer from, say they're just front loading all their nitrogen fertilizer up front. We don't want to take them from here to, let's just start with cover crops. We're going to cut out all that nitrogen and just do it all naturally. We don't want to do that because it creates so much risk and stress, and we don't want to do that. So the very first thing we want to do is improve the efficiencies of the system. So say, for example, we're currently applying a bunch of fertilizer up front, nothing else. Start a little bit up front, a little bit top dressing. We might do that for a season. Next season, okay, maybe let's put some foliars in. Okay, once we do that, then we can start doing these other things. We're going to improve the efficiency first so that we're not going to lose yield, and that's massive. So in terms of the efficiency, these kind of things are the efficiency side. Once we kind of get this nailed, then we can go to the substitution side. So in terms of substitution, we're going to be looking at biological nitrogen fixation. So this is a really useful way of getting nitrogen from our microbes rather than from fertilizer. So there's three types of biological nitrogen fixation. We have symbiotic, associative, and asymbiotic. Now, we all are familiar with the symbiotic. This is legumes, or the rhizobia bacteria that fix nitrogen for our legumes. We've got a whole video on nitrogen fixation and how to increase that, so we're not going to go over it quite here. So go watch that video out. It'll tell you everything you need to know about increasing the rate of nitrogen fixation in your legumes, things you need to check, and what you need to apply. But in general, you'd be able to fix around 100 to 200, even 300, maybe even more than that, per hectare of straight nitrogen. Now that's quite beneficial if you're growing a legume crop and you don't need to be applying as much nitrogen fertilizer, if any. But what we might want to do is think of this as either companion crops and sharing that through mycorrhizal fungi connections. We can also think about that in our cover crops. We can also think about that from a crop rotation point of view. So if we have a legume going to wheat, a little bit of that nitrogen will carry over as the roots decompose from the legumes. Not all of it, as a lot of that's going to be carried away in the legume product, but it can help. Legumes can fix, say, 100 to 300 kilos of nitrogen per hectare. Some of that's going to come over. Associative. So an example of this is Azospirillum, and you'll see a whole bunch of different species here in terms of the different bacteria. But this one, for example, has been found to fix between 10 and 40 kilos of nitrogen per hectare. And when we think about this, we could almost just, in terms of the efficiencies of this, we could almost just assume it's going to be double the efficiency because we're not going to lose it. So the replacement value of this fertilizer as urea could potentially be 20 to 80 kilos of urea because we're not going to be losing as much of it. So it's not a bad amount of nitrogen. Now, these are one of the things where it won't completely replace your nitrogen fertilizer. It's unlikely it will, especially if you're pulling like really high amounts of crop off your paddocks. So the example given here, this is 4 tons a hectare. Some people are pushing 8, 9, 10. The world record, I think, is 17 or so, or nearly 18. It's unlikely a natural system will be able to supply enough nitrogen in basically an unnatural system by itself. So nitrogen fertilizer still definitely has a place, but again, it's improving that system. But anyways, this will definitely help. 80 kilos of effectively urea for free is not bad. But anyways, about 10 to 40 kilos of nitrogen in a amino acid form. It's great for free. Now, associated bacteria, these are things where they're not inside the plant root, such as rhizobia bacteria. These are things that are living in the root zone that feed off the sugars of plants. So they're in that dreadlock of the plant, you'll find. They can also participate in the rhizophagy cycle, which we'll talk about in a moment. And really, the way to increase these guys is both by inoculation as well as actually feeding them with enough sugars. So we can firstly feed them with adding sugar to the paddocks, such as with molasses, but also with cover crops, actually having the root exudates there to feed these microbes. So that can be both from a cover crop or from the actual crop itself, feeding root exudates. And the other way to increase root exudates from the crop is increasing photosynthetic ability by supplying the right nutrition to it. Now, next is asymbiotic. These are things that don't even associate with the plant itself. So it doesn't quite consume or rely on the plant to supply carbon inputs, so root exudates. These things, they just chill out in the soil environment, doing their thing. So these are things like Rhizotobacter. They just hang out. They can produce around 20 kilos of nitrogen as well, a hectare per year. So pretty good. So both of these things together, you could probably fix somewhere in the ballpark of 10 to 50 kilos of nitrogen per hectare, potentially even more, just depending on your system. Obviously, this is dependent on carbon inputs, which is dependent on rainfall and temperature. So it depends on your area. So next is the rhizophagy cycle. This is where plants actually eat microbes by they go into their root. The plant rips off the cell wall, consumes those amino acids, and then spit them out. We've got a whole video on that, so we won't go too much on it now, but it can supply, in one study I found, it supplied 33% of the nitrogen requirements of, I think it was a tomato plant. Now, it's one of those things where it's very difficult to quantify how much your crop would actually benefit from the rhizophagy cycle. The thing is, it definitely will benefit. The question is, how much will it benefit? And that's what we don't quite know. Some people suggest that you can get 100% of the nutrient requirements from the crop from these systems. But if I was managing a $5 million crop of wheat, would I risk just relying on these things to supply it? Maybe not. And that's why we take different subtests to know exactly what the plant needs. So the rhizophagy cycle is definitely an important source. It's how do you stimulate that and how do you actually get that in such a way where you're not going to lose yield and make sure you're still getting enough nitrogen. And that's where, a combination of these things with foliar nitrogen is quite beneficial. So next we have our cover crops, catch crops, and just manure crops. So basically, they're more or less all the same thing if you're going to use it in this context of supplying nitrogen to the crop. That's making sure you got a bunch of either legumes in the crop to produce your 100 to 300 kilos of nitrogen per hectare, or just plants in general feeding your nitrogen fixing free living bacteria. So there's that component, as well as in the catch crop component of soaking up excess nutrients in the soil. So if you have a crop like cotton where you're applying a lot of nitrogen and not all that nitrogen is taking up, putting a catch crop in is quite a good idea because it'll soak up a lot of those, say, nitrates and ammonium, put it into amino acids in the plant form, lock them up, and when that cover crop or catch crop dies, it will then cycle through with microbes. And so the suggested turnover rate is about 1 to 2 months for microbes. But a good rule of thumb is that 50% of the nitrogen within that cover crop will be available within a year. So 50% in the first year, the following 50% of that will be available in the next year. So say you fixed 100 kilos of nitrogen, in the first year, or 12 months after that, 50 kilos of nitrogen will be available, in the next 25 kilos, in the next 12 and a half. So if you do this over multiple years, that will build up to effectively be supplying 100% of the nitrogen fixed by the cover crop. Now again, different cover crops and different species within the cover crop will have different amounts of nitrogen. So legumes, for example, might be pushing up into 3%, whereas grasses might be around that 2%. Likewise, the age of the cover crop will determine nitrogen lockup and the release of the nitrogen over time. If it's too mature, it'll take longer to release as there's more carbon. And you'll also get nitrogen lockup. If it's young, it'll release earlier. If you're interested in using cover crops, we have a free cover crop mixer on our website, so you can go there, you can put in your 3 different goals that you want your cover crop to perform, as well as any limitations from your soil and your environment. and it'll spit out a custom mix just for you with application rates, the ideal ratio of each of the ideal species in that mix. And then it also gives you a suitability. So it's really good. For this context, you can actually make it a goal for your cover crop to either fix nitrogen, and it'll do that. You can also make it as a catch crop by putting in nutrient recovery as a goal. And then finally, we have organic matter as it is, so the humus. Now that has about a turnover of about 2 to 3% each year. So 2 to 3% of the organic matter within that, which is about 5%, will be available every year. Now, it kind of depends. I wouldn't quite rely on that, and it depends on the seasonality, whether or not you've got warm and humid and wet conditions, which is going to increase the mineralization, or if it's cold and dry, it's going to reduce mineralization. The best way to estimate this is with a Haney test. The Haney test takes a water extractable organic nitrogen, which we used here. So this is water extractable, which means that organic matter is already, or the organic nitrogen is already in the soluble component of the water. We're not destroying the humus as it is. It's already in the water, available for the crop to use. The other thing is that we don't quite want to rely on this number because it can assume we're going to be mining soil organic matter. If we're just using water extractable, there's less chance of us mining our soil organic matter, which should make for a more sustainable practice. Now, one more thing with organic matter, we can also factor in, say, manures, so chicken manure or composts into that. Again, I'd say it's more like the cover crop. 50% of that nitrogen will be available within the next 12 months. So that's all our sources. Now we've got to try and fix our sources into supplying this 95 kilos a hectare. And so really it just depends on how you want to do it, enterprise you're in, whether or not you want to really just front load it all, in which case you just work out how much of a particular fertilizer you need to apply up front. I wouldn't recommend that. Split application's always better. But likewise, if you are happy to do a bit more work, doing a top dressing is the next one, then a foliar application, maybe adding some biological components to a seed coat, all of that plays into the program. And that's why it's quite beneficial to work with consultants like us at Agresol, because we can actually build this program out for you in a way that's built on science and not just taking a guess. Now, the other thing is that you can actually do all this math and everything in season. So for example, if we go back to our nitrogen budget, you can rework out your nitrogen budget and your target, or say you can rework out your target yield with the water rainfall so far. So if we go back to our target yield video, if you have had 50% less water or rainfall up to this point, you can use that rainfall data plus using the average in the future to then rework out your target yield and the amount of nitrogen you need to apply to that crop. So say, for example, our target yield has been downgraded from 4 tonnes a hectare to 3 tonnes because we had a bit of a dry start. We can do all this math to work out we only need to apply 54 kilos of nitrogen because we don't need that additional nitrogen for that extra kilo because we didn't get enough water anyways. And say we already put up 20 kilos of nitrogen per hectare, then we only need to apply 34 kilos left. So you can do this up front before getting into it, or you can do this, in season, month to month, to determine your next applications. So again, this is really important because it gives us an insight into the actual amount of nitrogen we need to apply to our crop. So we're not applying too much and we're not applying not enough so we get the ideal yield. So I mentioned differential sap tests, and we like to use differential sap tests before putting on a nitrogen application, just so we actually understand, does the crop need nitrogen or not? Because all of this stuff is kind of cool in theory. Yeah, we're going to get our 20 kilos here, and we're going to get, an additional 30 kilos of nitrogen per hectare from a cover crop we did, but we actually don't know what the plant is taking up. So we used a differential sap test to know exactly what the crop needs at that particular time, and that's super powerful to make sure we're hitting nitrogen. So as I said before, we take the young and the old leaf, compare them to come back with total nitrogen as well as nitrate and ammonium, and we can use the translocation of each or the mobility of each to determine whether or not we have a deficiency. And then we can use that to determine foliar application rates, even top dressing and all that. One thing that we like to do with that is we can use the nutrients in that differential sap test to help guide us in making nutritional applications which help defend the plant against pest and disease. So as I mentioned before, nitrate and ammonium in the plant makes for really good food for pest and disease. So what we want to do is, if we pull up our sap tests and nitrogen's fine, we don't need to apply nitrogen, but in terms of the totals, but our nitrate and ammonium aren't at 0. What we want to do is make sure we apply the minerals required for the plant to then take the nitrate and ammonium and convert it into amino acids and then proteins. So the big ones for that, to get nitrogen into proteins, is we need sulfur. So we talked about that in a bit back here. We need a 10-to-1 ratio of nitrogen to sulfur. We need magnesium. Magnesium for a few parts. Firstly, we need it in the glutamate synthase, which converts the ammonium into glutamate. So that's important, as well as in the ribosome, which takes the amino acids and attaches them onto the proteins. So that's important. We also want the molybdenum. Now, it depends what form. If the nitrate's high, then it's going to be a molybdenum problem. So we want molybdenum as well. And then to some extent, in terms of disease, or pest and disease resistance, we want to make sure we have enough boron too. So boron's important for the translocation of the sugars, as well as all the other minerals around the plant. So boron's important. On top of all of this, we want to make sure we have sugars, because sugars are the feedstock for our amino acids or our glutamate, which gets the ammonium added on. So that's quite important too. So we want to make sure all these things are present in the plant, and we can use a differential sap test to target which are deficient. Likewise with our sugar, that's going to be a function of photosynthesis, which is a function of all the minerals required for photosynthesis. Once we hit all these things, we shouldn't have as much pest and disease pressure, which means we don't have to spend as much on pesticides, which is great. Now, the very last thing I'd like to touch on is soil primers. So a soil primer is something you add to the soil to really stimulate the biology. Now, that's really important when we get down to the nitrogen, biological nitrogen fixation and the rhizophagy cycle. So we can add things like molasses, as well as humic substances. We can add kelp, fish, as well as fulvic acid and humic acid and humates. All these things, we can apply it to our soil to really get our biology going. We can do that 2 to 3 weeks before sowing, ideally before a bit of a light rain, to wash it into the soil and get those things started. That will help with all the biological side, which is super important. Likewise, we can add seed coats to help further that biology. One more thing, mycorrhizal fungi. That in itself doesn't fix nitrogen, but the mycorrhizal fungi can then form symbiotic relationships with other microbes, which can then fix nitrogen to then supply to the plant. So that's another way of extending the root zone effectively to then associate with more microbes. So that's super beneficial. A soil primer can also be used as a stubble digester, which can help with increasing the breakdown of our stubble. That can help with that cycling as well, and stimulating the microbes to then decompose that material to then release it to the crop. So a soil primer should improve the efficiency of the overall system, as well as release a lot of locked away minerals. So I hope that helps you understand a regenerative way to manage nitrogen. Again, this whole thing will be written up on our website, so you can refer back to it anytime. If any of this sounds interesting to you and you'd like to integrate this on your farm, feel free to reach out. We have our free regenerative consultations on our website. You can sign up. It's a video call with me. We'll go over some of these things if you're interested, or 5 or so different ways we can overcome your biggest limitations on your farm using a regenerative framework. Awesome. Thanks for watching. My name's Teal. Cheers.